We are recording.
I'm Brandon Nelson. This is Seth Fulton and Isaiah Ponce. And we have the forms of high and low temperature corrosion. And I'm going to talk about carburization first. And the definition is it's a formation of metal carbides in a material resulting from exposure to carbon-containing species. And it's also known as metal dusting, and that's a more extreme form of it. And that leaves a powdery substance on the substrate. I guess it kind of looks like chalking a little bit. Environments, it happens in process piping containing hydrocarbon gases. Carbon monoxide environments, so anything with methane, ethane, propane, susceptible metals. Steel alloys are pretty susceptible, and nickel and chromium are good at resisting it. And be on the lookout for carburization when pipelines containing gas mixtures of carbon monoxide and hydrocarbons. And as temperature increases, so does carburization. So as the temperature gets higher, it gets worse. And there's supposed to be a little more on that slide. Here's a picture. That's metal dusting, a microscopic image of it. Here's another one. As you can see, it's got a lot more grains in it, I guess you could say. And so carburization makes it a lot more brittle. There's another one. It causes pitting too. So there's a little pit right there. Testing methods, you use ultrasonic testing, and that's just used to see if you have any thinning areas on the metal. Mitigation methods, select alloys with sufficient resistance, and that's going to be nickel and chromium are the best for that.
So high temp oxidation. So what is high temperature oxidation? High temperature oxidation is the reaction between the metal and atmospheric oxygen at elevated temperatures. This usually results in an oxide layer or scale buildup on the surface of the oxidizing metal. And when I say high temps are primarily 650 degrees Celsius or greater. This is the red hot range, and sometimes it can range a little bit below that, so that's just like an average range. High temperature oxidation, the environments it's usually going to be in facilities where the pipes is touching or in contact with the atmosphere instead of below ground pipes. This is industrial processes, process boilers, refineries, chemical processing plants, in automotive. Susceptible metals and alloys, you're going to have iron, which when it oxidizes, it's going to have an oxidation. It's rustite, it's an effective oxide of iron. Iron-based alloys that contain carbon steel or molybdenum and tungsten alloying additions. When the molybdenum and tungsten are alloyed with iron, they're going to oxidize at a rapid rate. The causing factors, the driving forces, the interaction between the reactive or reducing gas environments and metals at high temperatures. You're going to have oxidation process where the oxidation atoms do not dissolve in the base metal, and oxidation process where the base metal exhibits solubility for oxygen. So this is going to be where either you're going to have oxidation on your metal itself or oxidation on the oxidation scale. So the oxidation scale is going to grow. So you're going to have really two areas where your metal is going to oxidation is going to happen. The corrosion cell mechanism will be in general function of the surface characteristics of the structure, temperature, the elapsed time of reaction, and the gas consumption, and pressure. Behavioral oxidation depends on the thermodynamics and kinetics, how fast your oxide scale is going to grow. And here's a picture of the process. So your metal is going to absorb your O2 gas is going to absorb in your metal, and your metal is going to give up. Your metal is going to give up electrons to oxygen, and it's going to become a more positive, electropositive. So then your cations is going to release cations, and your O2 is going to release anions, and then that's going to form your film scale. As you can see, the electrons are given up from the metal, and the oxygen is taking those electrons. Then you're going to form a scale right there. And if it's a carbon steel, you're going to have micro cracks because the carbon diffuses with the scale in the base metal in reaction with iron oxide to evolve CO2 gas, and that CO2 gas it's going to have a buildup, and then it's going to cause cracks in your oxidation layer in your scale buildup. The Ellingham diagram, this helps to visualize the relative stability of metals and their oxidized products. So the more energy released when forming the oxide, the more stable the oxide, which means the oxide's it's not gonna grow at a rapid rate. It's gonna grow, but kind of like at a constant rate. The higher the temp, more the oxidizing species is required to maintain the oxide or film. So the higher the temp, the faster the rate, or the more rate the chemical process is going to take place. So on this is the Ellingham diagram. You got your temperatures and then your thermodynamics. So the amount of energy released when it releases those electrons, and then you have your temperature. The higher the temperature, this is useful in predicting the conditions under which an ore will be reduced to its metal. So how metal oxidizes in its environments and how much energy is released from that metal. Here's some pictures of high temp oxidation. You can tell you get breaks in the metal when there's an oxide. If it's not a protective layer, so if it's like iron, it's going to oxidize, and that oxidized layer is going to build up to where all those electrons are being taken away, and then it becomes more weaker and weaker, and then deteriorates. Testing and monitoring, you can have test coupons. You can have automatic recording of balance. This is more of like a lab test. It detects spalling of small amounts of oxide layer and immediately registers the mass loss of that metal. And high-speed electrical resistant probes measures metal loss in real time. So you put that probe on a metal, and then it relates real time information to that database. The corrosion control methods: pick high temperature alloy coatings. They have coatings that you can paint on your metal that when it heats up, that coating kind of oxidizes itself, and it has like a chromium, or if it's aluminum or silicone based coatings, to where it protects the metal structure. Pick alloys that are nickel, cobalt, or chromium based, or stainless steels, because whenever they oxidize, they produce a protective layer that slows down the electron and the ion movements, so there's no oxidation. Super alloys resistant to oxidation at high temperatures, high temperature corrosion, higher proportions of refractory metals such as nickel and cobalt.
Next we got the high temperature hydrogen tag. Also, it's a form of decarburization. So those are kind of interchanged a lot. What it is a loss of strength and ductility due to a high temperature reaction with the absorbed hydrogen with the carbides in the steel, resulting in decarburization. Some of the environments, it's a very dry environment, and it usually starts around 700 degrees Fahrenheit is where you start to see it. As far as industry-wise, it happens mostly in the refinery. On the process equipment, it starts at heat exchangers, storage tanks, and furnaces. And on the heating, like the heat exchanger furnaces, it happens a lot towards the nozzle, towards the tip of it, where the heat comes from, and also occurs in welds. Some of the susceptible metals are carbon and low alloy steels.
most commonly carbon steel, and carbon half molybdenum steel is where it is most susceptible. Some of the general rules of thumb is you don't want to put it above the Nelson's curve, which I'll show you a picture of the diagram here in a second. And also it's a time, temperature, pressure phenomenon, which means the more time it's exposed, the higher the temperature is exposed, and the higher pressure rating it's at, the worse effect you're going to have. And here's a picture of the Nelson's curve. And you just want to stay, each type of metal has a different scale in there. You want to stay within the recommended by the Nelson's curve. Some of the factors that control it are the temperature. The higher the temperature, the more damage. The time, the more time exposed, the worse it'll be. That kind of goes back to the time, temperature, pressure phenomenon. Then also the content of the hydrogen. The higher the content is, the more corrosive, more damage it'll do to the structure. The corrosion cell mechanism, that formula right there on the screen is the formula for methane. Atomic hydrogen reacts with the dissolved carbon in the metal carbides, forming methane. So when that methane forms, because it reacts with hydrogen, it builds up the pressure and causes intergranular cracks in the metal. And here's a picture right here. That's just a general form of decarburization. And there it is in chromium steel. You can see the crack in that. It's pretty pronounced in the intergranular cracks. And here it is again in silicone steel. Some of the different testing methods. It is difficult to test because it can be localized. And the wet fluorescent magnetic particle test, it's non-destructive testing. What they do is they spread fine wet magnetic particles over the surface that's being tested. They do that while it's being magnetized, and the buildup of the particles will form at the discontinuities in the pipe, so the cracks in the pipes where it builds up at.
All right, and here's a dry corrosion. I did I skip something?
Yeah. The mitigation, avoid the high carbon steels and use a higher alloy content of more better metal. Follow the Nelson's curve. As we're talking about, you want to stay in the 30-degree range of that, of the 30-degree margin of that Nelson's curve is a general rule of thumb, and is the best way to ensure to protect your coating and protect the metal, and also use a high fusion of bonded epoxy coating as well.
And here's dry corrosion. It's another high temperature. The definition is a reaction taking place between metals and gases at temperatures above 100 degrees Celsius in the absence of moisture. The type of environments occurs in gas lines at high temperatures. Anything with oxygen, halogen, H2S, and sulfur vapor catalyst for dry corrosion. Susceptible metals and alloys, avoid the use of high carbon steel. Steel with low alloy content is susceptible to dry corrosion too. And any temperature above 100 degrees Celsius is going to accelerate. Testing methods, coupons are used and corrosion inhibitors are used just to keep control of the chemical content in the pipeline. And there's a picture. This is caused by carbon monoxide and oxygen. And that was caused by H2S. And here's another one with carbon monoxide. And here's a little corrosion mechanism right here. As you can see, the H2S gets into the substrate, and the iron is oxidized, and then hydrogen is released back to the substrate. And I was going to give you a little redox reaction right here, since we were going over that. And so here's, you got to figure out what your charges are on here. So hydrogen's always a positive 1. And you got 2 of them, so that's a +2. Since that's a +2, that sulfur is going to be a -2. And Fe, or iron by itself, is just 0. And so over here, the iron and sulfide, they combine, And the iron goes to +2, since you know that the sulfur is -2. So you want those to be balanced. And hydrogen gas by itself is always just going to be 0. And so looking at that, you know that iron loses electrons since it becomes more positive. So you know that's getting oxidized. And hydrogen started positive and then it went to 0. So you know it gained electrons, and so it's getting reduced right there. That's about it right there.
So internal oxidation. Internal oxidation is the process of oxide formation away from the material surface through the fusion of oxygen within the material. So on high temperature oxidation, you had oxidation scale buildup on the metal structure itself. This is going to be oxidation in the metal itself. Examples of this would be silicone and copper, where silicone's oxidizing is the alloying component that's being oxidized in copper, or chromium and nickel. This affects the microstructure of the material. So the environments, it's going to be a high temperature environment, 600 degrees Celsius and above, in heat treatment plants, refineries, mineral processing plants, susceptible metals and alloys. So copper when alloyed with small percentages of certain metals like aluminum, tin, titanium, zinc, silicone, and manganese. Your silver alloys, or aluminum containing nickel-based alloys. Internal oxidation takes place under the following conditions. These conditions are going to be when the alloying element has a greater affinity for oxygen than the base metal, where it oxidizes instead of the base metal. Diffusivity of oxygen in the base metal should be greater than that of the alloying element, and penetration of the internal oxidation inward should be faster than the rate of the scale formation. This is a picture of the corrosion cell. Oxygen, or in this case it's nitrogen, is being diffused into the alloy and reacting with the alloying components with higher oxygen affinity than that of the base metal before the alloying components can diffuse to the metal. So you have aluminum nitrate, right? In the middle, aluminum oxide and titanium oxide, nitrate, excuse me. And when that nitrogen diffuses into the metal, there's a base metal and then those alloying components, and those alloying components are oxidizing inside the metal structure. So you're not going to see internal oxidation with just your eyes. You got to have like a microscopic visual aid. And here's those little spots are the oxidation inside the metal. And here are some other pictures of oxidation, which can cause cracking and stuff like that, because it's forming holes of oxidation scale buildup. The corrosion control methods change microstructure of metal with heat treatment, control the concentration of oxygen in surface layers, high temp coatings, or assembling, and this was in the Black Bible, they assembled an active getter for oxygen, such as a strip of titanium that's going to take, leaving an atmosphere that is reducing to both components of the alloy. That's going to take, pretty much take the oxygen instead of the alloying components in that metal to be oxidized.
Next we're going to talk about sulfidation. Sulfidation is a reaction of the metal with sulfur to produce a sulfur compound that forms on or under the surface of the metal. There's some facts about it. It's a result of naturally occurring sulfur compounds that are found in crude oil, so it naturally occurs. And also, it is a form of oxidation. The environment, so it usually starts about 500 degrees Fahrenheit, about at 500 to 700 degrees, where it starts. Refineries. This is where sulfidation is found the most. This is the most critical industry that fights this battle. And it is because it is a naturally occurring compound that's found in crude oil is one of the biggest reasons they fight it. and it causes pipe wall thinning, and it's commonly found in the heater tubes and in the pressure vessels. It also occurs not only in the refiner business, but in jet turbines. The sulfur from the fuel burn off and the airborne salts react with the oxide layer on the blades, and it eats away at the aircraft structures. Sulfidation is allowed on jet turbines as long as it is as long as it covers less than 25% of their overall turbine. So it's not just the oil and gas industry that's fighting this too. Some of the susceptible metals are carbon steels with low alloy content. That's the majority that has this issue. But 300 series austenitic stainless steel is the best to use. And the reason for this is it has an 18% chromium content in it, so it's very high in chromium. Some of the general rules of thumb for sulfidation is anything under 500 degrees Fahrenheit is not a big concern. Now, however, it still is a concern. It still needs to be monitored, but it's less likely to have effect under 500 degrees. And carbon steel will usually be acceptable if it is under 500 degrees. It will usually be generally accepted to fight it. Some different factors that affect sulfidation are the temperature, the concentration of sulfur species, the flow rate. The higher the flow rate, studies show it seems to cause more of a pipe wall thinning, and also the alloy content. The mechanism, it is a form of oxidation, but it's much more destructive than oxidation by oxygen. What it does is the polarity of the metal is shifted in the electropositive direction, and as that happens, the corrosion rate increases. The more electropositive it goes. Here's a picture. This is at the Chevron refinery in Richmond, California, and this is actually, I believe, from 2011. And this is in their refinery, and that's the blowout they call sulfidation. And on this next picture, you can see as it gets closer to the blowout, up here it's got a 0.4 wall thickness, and down here the actual blowout it's a 0.003. So you can see that how much the sulfidation really does thin the pipe wall thickness a great amount. And here it is on the jet turbines, where you can see it builds up on as long as it's less than 25%, they don't really worry about it. Some of the testing methods, smart pigs are a good way. They can detect pipe wall thinness. And then high temperature weld detection, PMI inspections like X-ray fluorescent, hardness testing, the different file tests you can do, and optical emission spectroscopy. Different mitigations to use. It is hard to mitigate because it is a naturally occurring compound. But like I said before, you can use a higher alloy content of more acceptable metals such as chromium, nickel, and aluminum. The nickel and aluminum are more expensive, but those have shown to have greater deterioration of sulfidation.
All right, here's cold end corrosion. The definition is an electrochemical reaction that occurs on a metallic surface that is at lower temperatures compared to the dew point of the corrosive gas mixture to which it is exposed. Environments, it occurs in aeronautical engines, car engines, ship engines, water heaters, and boiler economizers, susceptible metals, steel, and pretty much any alloy that goes with steel. Corrosion indicators. If you have sulfuric acid in the pipeline or anything, it's a good sign that cold end corrosion will occur. And also hydrochloric acid and the hydrochloric acid too.